This was a no calculator question. Particle motion. A particle moves along the x-axis. The velocity is given by cosine of pi 6t from 0 to 12. When's the particle at rest? How do we know when a particle's at rest? When velocity is 0, right? So you had to set this equal to 0. So whenever you have an argument, it's not just like cosine x equals 0, but it's cosine stuff equals 0. You set the stuff equal to the angles that you know make cosine be 0. What's the first angle you think of when you think of cosine value of 0? No? Pi halves. 3 pi halves. 5 pi halves. Negative pi halves, right? Okay. All right, so we got that, and then you have to solve for t. So to solve for t, you just multiply both sides by 6 over pi. When you multiply this by 6 over pi, the pi's cancel. You get 6 over 2, which is 3. Here, you get 18 over 2, which is 9. Here, you get 30 over 2, which is 15, ... But we're only going for times from 0 to 12, so when is the particle at rest? The particle is at rest at t equals 3 and t equals 9 because v of 3 and v of 9 equals 0. Right? All right, so that was part A. Any questions on that? Part B, when is the particle moving to the left? How do you know when a particle is moving to the left? When velocity is negative, which means we might want to make a velocity sine line, right? All right, so good for us. We already found the critical values. So we have 0, 3, 9, 12. So this is our velocity sine line. So if I plug a number like 2 in for t, I get the cosine of pi 2 pi 6, which is pi thirds. Cosine of pi thirds is positive. If I plug a number in like 6, right, then I get cosine of pi, which is negative. And then if I plug in a number like 11, I get cosine 11 pi 6, which is fourth quadrant, so it's positive. All right, so when is the particle moving to the left? The particle is moving to the left from t equals 3 to t equals 9, or on the open interval 3 to 9, because velocity is negative on that interval. Any questions about that one? All right, good. Find the acceleration at time t. Acceleration is the what of the what? Derivative of the velocity. All right, so our a of t, derivative of cosine, negative sine. So you have negative sine of pi 6t, never change your argument, but then I got to multiply by pi 6. Got to multiply by the derivative of the argument. There's my acceleration done. Right? That's part C. Is the speed increasing, decreasing, or neither at t equals 4? Explain your reasoning. How do we know if speed is increasing? Good job, Casper. Yes, okay. Yes, velocity and acceleration on the same side, right? Decreasing when they have opposite. 4, right, is right in here. So at t equals 4, velocity is negative. We plug a 4 in to our acceleration function. A of 4 equals negative pi 6 times the sine of 4 pi 6, which is the same thing as 2 pi thirds. The good news about this is you don't even have to know what the sine of 2 pi thirds is. You just need to know if it's positive or negative. 2 pi thirds is in which quadrant? Second quadrant, which means sine there is positive. Are you sure?
Yes, it's positive.
I heard a mixed set of answers.
It's positive.
What's positive?
Are you sure?
Yes.
Yes. Okay. Sine is your psi y, right? Sine is positive when you're above the x-axis, negative below. Coho, Cosine is positive when your x's are positive and negative when your x's are negative. All right, so this one would be positive, but it's a positive times a negative, which means that our a of 4 is also negative. Therefore, our speed is increasing because velocity and acceleration have the same sign, or you could say they're both negative. That's a pretty straightforward particle motion problem. Any questions on that one? All right, good. So now we'll do our PBA, and then we're going to move into my favorite problem of all 6, which is the penguin problem. All right. Yes, we give you the final verbatim in advance. Yes. Yeah.
Sweet.
I know. They do that for the AP exam too. The College Board sends out the questions a couple days early. Yeah.
That's pretty good.
That's awesome. I'm glad they do that. Then you can study exactly the questions.
Yep. Okay. All right, so for this one, I'm going to actually show you the answer key because I don't have all the decimals in my head. Finding the area of R. So in order to find the area of R, you had to find this x value and this x value. So you had to find where your E function, there's your function, you had to find where that equals 2, right? However you chose to solve that equation, you solve that equation, you get those 2 answers. And on the answer document, that's not it, there it is. 0.446 to 1.554-ish, right? So anyway, so you can just write 3 decimals, but your calculator, you need to store more. So I would store them to letters, call them A and B. College Board called them P and Q and just called them P and Q all the way through, right? So anyway, but you have to find those x values, and then area is just the integral of top minus bottom, right? So it's just E minus 2. So your area for your first one was 0.514. Any questions on part A? That was calculator. Okay. All right. So here's the thing about part B. When you are finding the area of S, S is tricky because from here to here, we have the E function and the number 1, top minus bottom. From here to here, we have 2 and 1, top minus bottom. From here to here, we have E and 1, top minus bottom. So 3 different tops for region S, which means there's a couple of approaches. So one approach would be do the integral from here to here, plus the integral from here to here, plus the integral from here to here with the various tops and bottoms. So you'd add those 3 integrals together. These 2 regions do happen to be symmetric, so you could just take the first one, double it, and add this if you wanted to. But I wouldn't take the chance if I was doing it. I'd just do the 3. All right. However, the other way, which actually is a little bit easier, is to say, good morning, Charles. So the other method is to find the area of this whole region, right? Just go 0 to 2, kabam, right? Find the area of the whole region, and then subtract what you got in part A for R, right? Subtract that out, and what you're left with is S. So it's a slightly easier, it involves 2 integrals instead of 3, or 1 integral and just subtracting the number. So anyway, so for that, they put both ways in the scoring guidelines. So you have the integral of the whole region, e to the 2x minus x squared minus 1 from 0 to 2, minus the area you got in part A, so you get 1.546, or you add all 3 integrals together, and then you get 1.546. So either way. So that wasn't a tricky area. You could not, you could do it sideways, but it'd be really hard. If you wanted to do this with 1 integral only, so you wanted to do it sideways, doing this minus this from 1 to 2, it only involves 1 integral, but you have to solve this side for x Which means once you ln both sides, you have a quadratic, and you'd have to do quadratic formula. And then you would end up with two solutions with y's in them, and then you would have your two functions of one for a positive part and one for the negative part. So, anyway, or the right side and the left side. Yeah, I wouldn't do that. I would not suggest that. But it would work, right? It could be done. All right, the last part. Write an integral expression that gives the volume of the solid when r is rotated about the line y equals 1. So we're revolving this region about that line. What method is this? Washer. Tell me what we use shell. Vertical axis. Vertical axis is best for shell. Yes. Okay. So for this washer, you start at your axis. You go up to the farther away boundary. That's big R. Axis, nearer boundary. That's little r. So our volume, pi, don't forget the pi, integral, it's P, what did they use, P and Q? I don't remember. Yeah. P to Q of, so big R would be your E function, 2x minus x squared minus 1 squared minus, and then 2 minus 1 squared. Okay. So make sure you are comfortable with area, disk, washer, and shell, and cross section. Any of those are fair game to show up on your final. Okay. Okay. All right. Okay, number 5. Number 5 is a very, very important problem to be able to solve. This problem, not this exact one, but a problem of this type has shown up on every single AP exam for at least the last 20 years. So it's really important to be able to do these. They have slight variations from year to year, but almost every one of them involve the same thing with a rate of stuff going in and a rate of stuff coming out. So we've done a number of these. We did drain pipes and gravel piles and like rock concerts. I think we did an amusement park. So all kinds of different problems, same context, same type. So in this case, it's penguins. So the penguin population on an island is modeled by a differentiable function p of t. P is the number of penguins. T is time in years over a period from 0 to 40 years. At time 0, there are 100,000 penguins on the island. The birth rate is modeled by B of t, and the death rate is modeled by D of t. Penguins are born, penguins die. All right. Part A, what is the rate of change of the penguin population at time 0? Part B, to the nearest whole number, what is the penguin population at time 40? Part C, to the nearest whole number, what is the average rate of change of the penguin population from 0 to 40? And to the nearest whole number, find the absolute min and max of the penguin population from 0 to 40. Show the work that leads to your answers. Now, you have options for doing this problem. You can do this individually. You can do this with your groups. You can do this on paper. You can do this on whiteboards. Whatever works best for you. Take the next 10 minutes and see what you can find out about these penguins. Go. Okay, so the rate of change of the penguin population, that's the rate that they're born minus the rate that they die. So if you're looking for P prime of t, that would be B of t minus D of t. So we wanted at time 0 So P prime of 0 would be B of 0, which is 1,000, minus D of 0, which is 250. So at time 0, the rate of change of the penguin population is 750 penguins per year. So at the beginning time, like the moment they start analyzing these penguins, studying the penguins, the instantaneous rate of change at time 0 is an increase of 750 penguins per year. All right, so that's part A. So part B, to the nearest whole number, what is the penguin population at time 40? This is, to me, the most important part of the question. So we want to find a function for P of t. So P of t, I'm going to try to squish this in here so that you can see it. Yeah, this is a PDF. I can't change it. So P of t, well, let's see. It's how many penguins we started with. How many did we start with? We started with 100,000 penguins. Then you add how many penguins are born from, we just wanted it from 0 to 40. So we'll say I'll put P of 40 here. You could do a P of t, but we'll do P of 40. So P of 40. So we start with 100,000 penguins. Then you add the total number of penguins that were born, right? And then you subtract the total number of penguins that died. Right? So it's 100,000 plus the integral from 0 to 40 of B of t. That would be the total number of penguins born. So if B is the rate of change that they're born, then the integral would be how many were born, right? And then minus, if D of t is the rate of change at which they died, the rate at which they died, then the integral of D of t would be how many died, right? So start with 100,000, add how many were born, minus how many died. I don't know the answer, but I have the answer P. So, and it had to be rounded to the nearest whole number. So 133,058 penguins are on the island at t equals 40. So 1, 2, 3. Not everybody's working on whiteboards, but at least 3, 4 groups. Good, good. Okay, at least 4 groups got it. So that's good. All right. Okay, part C. To the nearest whole number, average rate of change of the penguin population from 0 to 40. Guys, go with the easy formula. If you're going to do average value formula, that's fine, but make sure you do it properly. So, do you want me to show you both ways, or do you not care? So, A-Rock, I'll show you just our old A-Rock would be the number of penguins at P of 40. I'll write it out. P of 40 minus P of 0 over 40 minus 0, right? So we'll put approximately 133,058 minus 100,000 over 40 minus 0. So it's whatever 33,058 over 40 is, which, so you get 826.45, but you had to round, so it was 826 penguins per year. So good. Good. Fantastic. Well done. All right, so good job. You guys are doing really well. All right, the last part says to the nearest whole number, find the absolute min and max of the penguin population from 0 to 40. So the first thing when you're finding maxes and mins, you find your derivative, you find your critical numbers, and you test your critical numbers and your endpoints, right? So we need a derivative for P prime. Lucky for us, in part A, we found P prime. P prime was B minus D, right? Rate of change of the penguin population. So what are we doing? We want to know when this is 0 or undefined. It's never undefined. So we're just looking for where this equals 0. I have no idea. I'd have to look. So, okay. So B minus D equals 0 at this 34.657, right? Okay. So then you need to test P of 0, P of 34.657, and P of 40. P of 0 is given, 100,000. P of 40 you found in part B, 133,058. The only one you actually have to do then is P of this 34.657. And in order to do it, you're doing this thing right here, except instead of putting in a 40, you're putting in a 30 whatever 0.658, right? So you do that to find how many penguins there are at that time, which is 139, 166, and 2/3 of a penguin, right? And again, the College Board rounded or truncated. They don't care if you go up or down for whatever reason you want. But anyway, so they rounded up. They called 2/3 of a penguin, right? Okay. So anyway, so your minimum population is 100,000. The maximum population is 139,167 penguins. Look at that. That's perfect. Well done. And you fit it all on that little tiny whiteboard. That's really impressive. All right. So, what? You drew a clock? Okay. Got it. All right. So, there you will see one of these sometime in the not too distant future, probably. If not tomorrow, then certainly next semester on your final and your AP exam. So anyway, okay. All right, last question, much shorter, much faster. So it's a table 3 months on kind of a question. I'm going to read it to you, and then I'm going to give you another maybe 8 minutes to see if you get this one done. Hang on a minute. So notice it says the twice differentiable function W. They don't say that unless you need it. Okay. Models the volume of water in a reservoir at time t, where it's supposed to say W of t. The t got moved to the next line, but this t is connected to the W there. All right. Where W of t is measured in gigaliters. Gigaliters means a whole lot of liters. Okay? And t is measured in days. The table above gives values of W prime sampled at various times from 0 to 30 days. At time 30, the reservoir has 125 gigaliters of water. Part A, use tangent line approximation at time 30 to predict the volume of the water at time 32. Show the computations that lead to your answer. Think about where you want the tangent line and then what you're plugging into the tangent line. Part B, left Riemann sum with the 3 subintervals indicated by the data in the table to approximate the integral from 0 to 30 of W prime. Use this approximation and maybe a little bit of other information to estimate the volume of water in gigaliters at time 0. Show the computations that lead to your answer. Ooh, part C, my favorite part. Explain why there must be at least one time t other than 10 such that W prime equals 0.7. I'm thinking theorem. Okay. And then finally the equation A equals 0.3 W to the 2/3 gives the relationship between the area of the surface of the reservoir and the volume of water in the reservoir. Find the instantaneous rate of change of A with respect to T when T equals 30. So I'm going to give you till 10:15. See what you can get done with this. Use tangent line approximation at T equals 30. What do you think's needed for a tangent line? Point and slope. The point, where do we get the point from? Is that the 30, 0.5?
No, it's the T.
31.25.
Oh, what's this 0.5?
That's the slope.
That's the slope. Because that's your W prime, right? Okay. So that's your slope. And then that's your point, right? So your answer would be, I don't know if you use Y or W. So W minus 125 equals 0.5 times T minus 30, something along those lines. And then to use it to approximate how much is there at T equals 32, you plug in a 32 in for T. So you get W equals 32 minus 30 is 2, half of 2 is 1, so it would be 1 plus 125. I get 126. Did they ask for units? Nope. I would say gigaliters, but yeah, 126. Yes, Keegan?
We put X and Y for equations.
That's fine. I would put Y and T instead of Y and X, because the T, no matter what, is a T value. The W is an approximation, so I would totally see replacing the W with a Y. Yeah.
But you wouldn't like to deduct them.
Probably not. I would think so. You probably wanted a squiggle equals when you do it. Like I used an equals, but you probably should use a squiggle. You want me to show you what they did? I have no idea what they used. They used W and T. Oh no, they used Y. They used Y and T. Y and T. To show that it's not an exact W, right? It's an approximation. All right. Okay. So there's part A. Part B, I'm going to erase part A just for space. So part B, use a left Riemann sum with 3 subintervals. There's your 3 subintervals. So we're going to say the integral from 0 to 30 of W prime is approximately. All right. Are these equal widths? No, you gotta do each one separately. What's the width of the first rectangle? What's the first height?
0.6.
What's the next width?
12.
What's the next height?
0.7.
What's the next width? Next height? 1. Alright, and then if you work that out, you get 22.4. 22.4. So your left Riemann sum tells you that from 0 to 30, the net change in the amount of water in the reservoir is 22.4 gigaliters. That's not how much is there. That's the net change of how much is there. That's how much, like, technically it's a net increase. All right. So use this approximation to estimate the volume of the water in gigaliters at time 0. So whenever you have to find an antiderivative amount at one point, that's a definite integral kind of a question. This is the kind of thing where we say, hey, look, ending amount equals starting amount plus the net change, right? Kind of a thing. If that throws you off, think of it like this. The integral from 0 to 30 of W prime. Well, what is that? Not in numbers, but in function mode. That would be W of 30 minus W of 0, right? Just evaluating your definite integral. So this definite integral you just said is 22.4. And then W of 30 you know is 125. W of 0 is what you're trying to find. And you just solve the equation. So W of 0 would be, move that, it's 125 minus 22.4. So 102.6? 102.6. All right, so that's your W of 0. So at time 0, there are approximately 102.6 gigaliters of water. All right. Part C. Explain, this was the one I heard the most discussion about when I was walking around. Explain why there must be at least one time other than t equals 10 such that W prime equals 0.7. I get that W prime is a rate, and you guys have memorized rate goes with MVT, But if you look at what your table supplies, what is this line right here? Are those W values? No, those are W prime values. So think about this. If this is W prime, and we're asking you, hey, besides t equals 10, is there another time where W prime has to equal 0.7? Where do you think the 0.7 would have to fall? Between 22 and 30, right? Okay. Is that an IVT or an MVT? IVT. You're trying to show that some value falls in between two other values on a table, right? So it had nothing to do with finding rates. It had to do with just saying, hey, look, 0.7 looks like it would fall right there. So how do we justify it? What's the first thing we write no matter what theorem we are using? Continuous, right? So we don't say W is continuous. We're not talking about W. We're talking about W prime. W prime is continuous on, and I'm going to look at this part right here on the closed interval 22 to 30. Check. How do I know that W prime is continuous? Because it says right there that W is twice differentiable. Right? Okay. All right. Next for IVT, you got to show that the 0.7 falls in between the endpoints. So I'm going to say, hey, W prime of 22 is greater than or equal to 0.7, which is greater than or equal to W prime of 30. Something like that, right? Or you could say this equals 20, this equals 1, and this equals 0.5. I don't care. Like something so that you have indicated that 0.7 falls in between. Okay. And then you have to write your conclusion. That's it. Check, check, conclusion. Therefore, by the IVT, name the theorem by name, and then rewrite the question without the explain why part. There must be at least one time other than t equals 7 such that W prime equals 0.7 today. You just rewrite the question. Yes?
Can you quickly refresh what NVT states and what EVT states?
I would be happy to. Yes. The big four. All right. Let's walk through the theorems, theorem by theorem. I'll take a second. EVT, one check, continuous on the close. So if your function is continuous on the close, that means the function has to have a max and a min on that closed interval, right? Absolutely. Max and min. All right, so that's EVT. IVT we just did. Continuous, and does the value you're interested in fall in between the endpoints of your interval, right? If that's true, then yes, it has to be there, right? Really what IVT says is that a continuous function has to hit all the y values in between any two given y values, right? To be continuous. To get from A to B, you got to hit all the y values in between. All right. MVT, two checks. Continuous on the closed, differentiable on the open, and MVT says that your AROC has to equal your IROC. So somewhere in that interval, if you find the average rate of change over your interval, somewhere in that interval, the instantaneous rate of change has to be equal to the average rate of change. That's MVT. Rolls, which is just a special case of MVT, says that if your function's continuous on the closed, differentiable on the open, and your y values at the endpoints are the same, that means your average rate of change is 0. So somewhere in there, your derivative has to equal 0, right? Your instantaneous rate of change has to equal 0. All right, so there's your theorems. The only, I will tell you, EVT, IVT, MVT, you don't have to state or know roles by name. You can always use, the College Board never uses roles. They always use MVT, but you can, right, if you want to. So that's an option. But if you don't ever learn roles, you can still get all your theorems right. Oh, wow. Okay. Thank you. Okay. Do you want to take this with you? I don't know if you might need it. All right. Okay. Very last question, which you may not recognize, but this is related rates, right? This is how the College Board asks related rates now. So we have a relation between area and volume of the water in the reservoir, area of the surface and volume of the water, and you want to find dAdt, right? Related rates, you're just differentiating both sides with respect to t, so really it's just checking to see if you know how to differentiate implicitly. So dAdt equals 0.3 times w to the 2/3 would be 2/3 w to the negative 1/3 times d w d. All right, so there's your general dAdt. We want this when t equals 30. So at t equals 30, does that mean I plug in a 30 for w? What do I plug in for w when t is 30?
125.
125, because that's what w is when t equals 30, right?
Yeah.
And then what do I plug in for dw dt when t equals 30?
0.5.
0.5, because that's what dw dt is when t equals 30. Does that make sense?
Yeah.
Yep. All right. So here, I don't have a final. Let me give you a final answer. If you want to see numbers. Final answer was 0.02. If you did, it was a calculated question. You could use 2.
That's
Okay. All right. But just doing the dAdt was 2 points. 2 points out of the 3. Okay, good. That is that.